I regret doing that because that like just hit the tickly part of the throat. So you can see the example where we talk about converting into spherical coordinates, because you see this monstrosity of an example. Like I said, it ain't pretty, but maybe we could do something with this, but we're going to have to look at all of those bounds, right? Because we're integrating x squared plus y squared plus z squared over the bounds related to z, then x, then y. But that x squared plus y squared plus z squared almost isn't really even relevant, right? Because that's just the function on top, you know, quote unquote, on top of the volume, not physically on top of it, but like the add-on function, right? So if we're talking about volume and we multiply it by density, then you get mass. So maybe that's a density function with the volume being the x, y, and z. You know, it could be anything, right? So, you know, I found a problem for one of my calculus classes years ago that talked about the density of traffic through the Lincoln Tunnel over a certain period of time. And I thought it was a fascinating question. And I spent like 6 months trying to find the data that led to the construction of that function. And I couldn't find it. So I thought, all right, well, maybe I can collect it myself over time, just based off of the traffic report. And so I tuned in to like 1010 wins or 80, I forget which one it was, years ago. Just at the same time every day, just waiting to see what the delay time was on the Lincoln Tunnel. And so I got the time elements of it, but I never got the what that would translate to in terms of density. And then I got to admit, I kind of lost interest after a period of time. But that's an element of density that doesn't have necessarily a geometric feel to it, but it definitely has geometric applications and a geometric representation. It doesn't seem like it would be. You know, like when they talk about the traffic report and they say there's high volume of traffic on the road today, it's like, are they talking about the same volume? Are they using the word volume appropriately? You know, and so and actually, fun fact, they're not. Right? It actually should be density, but it's interesting how they incorporate that. And then, you know, volume to represent sound, and you know, so there's so many different ways that you can categorize this, not just to say length, width, and height. Right? So that's why we don't want to just fall in love with the 3 physical dimensions. It could be 3 abstract dimensions. Right? So, but what we want to do is start visualizing. Let's just focus on the bounds, one thing at a time here. Right? So with each subsequent bound being a restriction on the previous one. So I have z. I had a moment where I thought I wasn't recording, so I wanted to make sure I am in fact recording. All right, so z is equal to x squared, 18 minus x squared minus y squared. So I can go through the process of trying to find a substitutable value for x, a substitutable value for y, or what I can do a lot simpler is square both sides. I'm just kind of rely on what we learned on the previous page. If I add, oh, sorry. If we add the x squared and the y squared to both sides, x squared plus y squared plus z squared is equal to 18. That's the definition of rho squared. All right. If I want rho, I just root that. All right. So that I look at the lower bound. And then what's that? All right, because we're bounding z somehow in terms of phi, I don't know about that. Right? What's going to happen here is you got to look at this and say, not that z is a straight analog for rho and somehow x is an analog for theta and y is an analog for phi. It's more like collectively xy xy and z are analogous to rho, phi, and theta, rho, theta, and phi. So we don't want to cast judgment on what's happening here until we see the whole picture, both literally and figuratively. Right. So we're going to take a look at the z equals the square root of x squared plus y squared. If it's too small, that's what happens, I guess. Now I could convert it over into cylindrical, cylindrical coordinates. But I also have a nice rule staring me right in the face here. It says z, well, it will say in a second that z is equal to phi sine, rho sine of phi. Right. So that's this bad boy right here. Right. And so that allows me to make the substitution for the radical x squared plus y squared and convert it over and make it equal to z if I want. Right. I could also say that the square root of x squared plus y squared, you know, as we know, is equal to rho sine of phi. We can do that too. But we have a substitution. It allows us to say that z can now be thought of as rho sine of phi. All right. So we want to be also thinking about, well, okay, well, what kind of figure is that? All right. So if we know that z is equal to the square root of x squared plus y squared, we also have the rectangular understanding of this that allows us to get a sense of what's happening in spherical coordinates. And so another thing that you could do is take this and square both sides. Z squared is equal to x squared plus y squared, and get everything over to the same side. Same side, and you'd have x squared plus y squared minus z squared is equal to 0, which should look awfully familiar. Right? That's a value that we had for phi on a previous page, on the previous page. Right? That we're looking at a hyperboloid. Right? So we can make the substitution, at least partly, by starting down the pathway where we replace z equals the square root of x squared plus y squared with z equals rho sine of phi, and then go from there. Like, for example, we know that z is equal to rho cosine of phi. In which case we would be looking for unit circle value, not unit circle values, acute angles where cosine and sine are equivalent to one another. We could do it that way. Either way, we should be coming up with phi is equal to pi over 4. All right, and that's based off the prior knowledge or knowledge of trigonometry. All right. Now, if you don't happen to know what the value is that would allow sorry, cosine to be equal to sine, then you can kick over to Desmos. You can pull out a unit circle. I know it's not in terms of theta, but it's still essentially the same relationship. You can also look at this picture that I still have up from the last time we did this. And you see that we have those linear relationships that make up the profile view of the hyperboloid. And so if you take a look at that, we want to be looking at it, I almost brought it to the wrong perspective. We want to be looking at it as an angle off of the z-axis, right? So if you're thinking about it as an angle off of the z-axis, I'm gonna have to snip it and bring it in. We know automatically it's going to be a constant value. It's just a question of what that constant value is, right? So once you recognize that it's a constant value off of the z-axis, it's just a matter of just coming up with that value itself, right? So let me just bring this in a little bit. There's no good place to put it, so I'll just kind of chuck it over here. But that phi value that we're interested in would be this one. Well, this is the definition of phi. All right, so that's what we're looking for. Since it doesn't change no matter where you are, to get to that most extreme portion of the region, phi would have to be whatever that angle is based off of this relationship. So if you know it's a hyperboloid and you know you're looking for an acute angle, then you would just be looking for the acute angle that allows cosine to be equal to sine. And if you don't know that that's pi over 4, that just kind of glitched. That's great. Yeah, man, get back in there for a faster experience by shutting down immediately. Oh, this is great. The only good thing about it is at least I didn't lose all of it, which I mean is a pretty solid thing to have as a consequence. But you could say, like, for example, y equals the cosine of x, create that graph. Excuse me. Y equals the sine of x. Restrict the domain to the first quadrant of the unit circle, which would get you from 0 to pi over 2. And we'll say -1 to 1. So where would they be the same? They'd be the same at that location, which has an x value of pi over 4. So either way, you're going to get a result of pi over 4. All right, so we're slowly starting to piece it together. All right. Now, we also want to get an idea of what on earth this volume is really talking about bounding. All right, so back to GeoGebra we go. I got to do this little tug of war here. All right, so I have, and I'll put it in its original form. We have the z equals, we knew the first one was a sphere. Or the top bound, if you will, was a sphere. The bottom bound was the hyperboloid. And now, based off of experience, hopefully you'll kind of carry this into the future and say, okay, if I see z equals the square root of x squared plus y squared, I know it's a hyperboloid, or anything in that form. It's just a question of what sort of hyperboloid, right? So we're talking about capturing the region based off of the constraints between x and y. We're going to get restricted, possibly, but the region with the low end being the hyperboloid and the top end being the hemisphere. All right, so we have that information. So we want the volume that's captured in between those two. So that tells me that I want to do one of two things in terms of phi. If I'm looking at this as the profile view, I'm either going to want to go, this is pi over 4. This is negative pi over 4. I'm either going to want to go from negative pi over 4 to pi over 4, or I'm going to want to go from 0 to pi over 4 and double it. All right. So depending on what I consider to be the easier route, I'll withhold judgment, but at least now I know the bounds for phi. It's based off of personal choice. It's either going to be negative pi over 4 to pi over 4 or 0 to pi over 4. So I have the z bound, the phi bounds. I have one of the bounds for rho. We're going to work on the second one. Based on the diagram, it seems like we're off to a pretty good start. I want to be thinking about the x and y bounds now. Right? Those are a little easier to conceptualize because, yeah, we can convert that over into the phis and rhos and all that stuff, but we could also just think about what it would be in 3 dimensions, right? And just play it out that way. So this x squared, or x equals 9 minus y squared under the radical is the same as saying x squared is equal to 9 minus y squared, or x squared plus y squared is equal to 9, which is a circle, right? So this is saying that my x values are going to go from the x value of 0 to the outer circumference of a circle, right? So let's take a look at that circle, which would have a radius of 3. So I'm going to draw a radius of 3 circle. And the one thing you never want to lose sight of when it comes to spherical coordinates is that theta, I always say it this way, it sounds weird at first, but eventually it starts to stick. Don't forget theta is equal to theta. And people are like, oh, okay, duh. But it's more like the way you've always thought about theta is the way you will continue to think about theta. All right. So when we look at this in rectangular coordinates, we are going from x equals 0 to the outer edge of this circle. So here's x equals 0. Now moving along in the x direction, we're going to max out once we get to that circle, that circular circumference. But then we're bounded between the y value of 0 and y equals 3. All right. So we're within the circle, bounded really by the x and y axis. So we're looking at just this region here. Right. So if we want to be thinking about what that would be in cylindrical or polar coordinates, we'd be saying, okay, well, our R value is going to span out. So cylindrical, now I'm thinking cylindrical, or R value would span out from 0 to 3. That's great. But what would our theta do? Our theta is only going to go from a value of 0 to a value of pi over 2, right? Based off of those restrictions, right? So that's what my theta is going to be. So now I have bounds for my phi. I have bounds for my theta. The only thing I'm even remotely concerned about now is what's going to happen with my rho. So the rho is the length of the distance from the center to any point in the bounded volume, right? So, well, what's the smallest that number could be? It seems like if I'm restricting really just to the first quadrant, really first octant, so between red and green, so I could trim this. I don't think I've showed you how to do that yet in person. I'll show you that in a minute. Oh no, it's 7:40. I'll show it to you first thing next time, because I also have to talk a little bit about the tech assignment too. But if we're living in the red, between red and green here, in that bounded region, right? Extending upward in that triangular fashion along the XZ plane and the YZ plane, we're still going to have the smallest possible value of rho being 0, because the point of that cone is right at the origin, right? And if you're in doubt of that, substitute 0 into the cone equation, 0, 0, 0 into the cone equation in rectangular coordinates, and make sure it checks out, and it does. So 0, 0, 0 is a valid point, and so therefore we could assume that the smallest value of rho is going to be also 0. All right. So then the only thing that's left to do is convert this guy over, but that's the easiest thing here. I saved the best for last. All right, that's rho squared. All right. So what we would get here is a triple integral. The substitution, and I do have to talk about this, but we were a little pressed for time, so I didn't want to rush it, but I also don't want to ignore it. The substitution for dx, dy, dz, and all its permutations is rho squared sine phi d phi d rho d phi. I'm staring at 2 p's there, and it's just aggravating the living daylights out of me. I can't believe I messed that up. I know what I did. I just got lazy, and I couldn't find the when I was typing this, couldn't find the row, and I just put a p in there saying, "Oh, I'll just change it later," and I just forgot to. Right, but those are supposed to be rows, so I'll take those as typos, of course. But those are the substitutions, the values that we use to substitute in place of the dx, dy, dz, and all its permutations. All right, so we'll talk about that next time. But for now, we're just going to kind of rely on it as a fact. No, I don't like to do that, but that's kind of where we're at. All right, so we have a rho squared, because that's the function that represents the integrand. Then we have a rho squared based on our relationship here, a rho squared sine phi, then d rho d phi d theta. All right, so that's the replacement for dx, dy, dz. All right. And the order of integration here is fixed as rho phi theta. There are circumstances where it changes, but not for our purposes, not yet. And so rho is going from 0 to rad 18. Phi is going from 0. I'm going to go 0 to pi over 4. Knowing that whatever I get as a result, I'm going to have to double. Right? And then my thetas are going to go from 0 to pi over 2. All right. Now, it could have been a case where we just went from negative pi over 4 to pi over 4, but if it's something that we had to do out by hand, it's nice to have lower bounds equal to 0. That's the only reason why I made the decision there. All right. So, and then let me just make sure of something conceptually. Oh, no, we don't need the 2. Just realized it. And the reason why is because this piece, as it turned out, became irrelevant based off of the restrictions due to X and Y. Right? Because we're living in the first octant, we never go beyond the acute representation of phi. So it's actually a good thing that we held off on making our integral until after we evaluated all of our different variables. So that was important. And actually, believe it or not, that was the reason why I didn't do it at the time. I just forgot again. Right. So yeah, definitely kind of a tricky concept, at least when you get started on it, but it gets more and more comfortable as you go. So yeah, well, what I'd like you to do is just try number 2 before next class. It's actually a much simpler version of this one. The bounds are unrestricted, right? So unrestricted bounds in spherical coordinates. So just keep that in mind, which means that whatever the bounds are for a sphere are what would be in play. So so yeah, it's kind of an interesting one. Except of course the relationship that x squared plus y squared plus z squared has to be less than or equal to 1. So that's the only thing you got to keep in mind. But it's kind of a weird problem, but it's very doable. Otherwise, if you don't like that one, give number 3 a shot, because I'm definitely going to go over number 2 with you. But number 3 is something that you could also tackle, because it's very similar to what we just did. Right. So if you want to actually, I would say probably try number 3 first before you try number 2. Just to get a kind of a good feel for how this stuff works. And then yeah. All right, so that's where we're going to end it. Let me stop the recording. I'm going to make some like honey tea and lay down.